Berkeley to give the CITA podium. Sukanya actually originally graduated from Berkeley under the tutelage of Frank Shu and Chris Keith, and then she went off to CFA to work with alternatives and that her empire. So then she came back, she saw the light of the East Coast, went back to the West Coast, and now back in Berkeley as a UC President's Fellow, and she's working with Leo and Frank Shu and myself on using dwarf galaxies, finding dwarf galaxies by looking at the tidal impact on the primary galaxy. Okay?
Thanks a lot, Phil. It's great to be back here. Last time I was here as a grad student, and I also visited in the winter when it was extremely cold. I was freezing because I was coming from California. However, Norm Murray, who is not here, informed me that it isn't cold until your nose hairs freeze. So technically, it wasn't cold enough. But it's great to be back. I want to talk about a new method to quantitatively characterize dark matter-dominated dwarf galaxies purely from analysis of observed disturbances in the outer gas disks of spirals, without requiring any knowledge of the optical light from these systems. And many dwarfs have very low light to mass ratios, so it's useful to have a method that doesn't rely on their optical light. Okay, so the idea here is to use the cold gas as a test of the perturbing effects of dark subhalos or dim dwarf galaxies as they're tidally interacting with the primary galaxy. So we're going to be looking at observed H1 maps, such as this one, then 51, and we're going to try to see what we can back out about the companions of these systems, purely from the observations of these kind of disturbances that we see. Okay? But this asymmetric feature we see in the H1 map of M51. And what I'll show is that from this kind of analysis, you can quantitatively infer the masses of satellites, their current radial location, and their azimuth. This is the observed H1 map of M83. The scale here is about 100 kiloparsec. Okay? So these disturbances you see really are on the outskirts. The optical radius is here. And I emphasize outskirts because that's where the effect of perturbers is dominant over the intrinsic response. So you can more cleanly disentangle the effect of perturbers if you're looking at the very outskirts of spirals. So Norm, I just said that last time when I was at CITA, it was really cold. I came as a graduate student, but you said it wasn't cold until your nose hairs freeze. So it's much better to be here now in the fall. And then I'll talk about the work that started the development of this method, which are the observed H1 map of the Milky Way. These are observations done by Azimuthal and Hellas. Note that the solar circle is here. So these disturbances that you see in the outskirts of the gas disk of our galaxy are really on the outskirts. I'm going to start with the proof of principle of the method first. Now this is actually going in reverse chronological order. So the idea here is to take a look at galaxies such as M51 with known optical companions and do kind of a double blind test. Okay, so we're going to pretend like we don't know about the satellites, and we're going to see what we can back out about the satellites just from analyzing this H1 map. And once we've convinced ourselves that the method works, we apply it to galaxies with known optical companions, we're going to go back and do the case of the Milky Way that really motivated the development of this method. I want to start with the history of dark matter. This very inspiring example of the discovery of Neptune in the 1840s by Leverrier, this handsome guy here. So in the 1840s, Leverrier analyzed disturbances in the orbits of the then-known planet Uranus, and he said there had to be another planet that was producing those disturbances. And he was able to calculate the azimuth of that planet, now known as Neptune, to within a degree. This was a huge success of Newtonian mechanics at that time, and as far as I know, it is the first example of the discovery of an essentially dark object by analysis of its tidal gravitational effects on another body. And it's in a similar spirit to the work that we're trying to do to characterize dark matter-dominated objects from analysis of observed disturbances in gas disks. Now, of course, we're motivated by cosmological simulations such as this one. This is a movie from Via Láctea. These condensations that you see here are dark subhalos, which are analogs to dim dwarf galaxies, and they populate all scales from very large scales to small scales. When you look at their distribution, the distribution of these subcumulus, it follows a power law. And when you compare their distribution from, when you compare the distribution of these subcumulus in simulations to observations of local blue dwarfs, you see that simulations far overpredict the number that are actually observed, and this discrepancy is come to be known as the missing satellites problem. So in this context, it's interesting to ask the question, well, where are all the rest that we expected to see, theoretically? And more broadly, the question I'm interested in asking today is, can you find dark galaxies by their interaction with gas disks? Now, people have looked a bit at the signatures of CDF substructure of the collisionless components of galaxies on stellar disks. This power law, the distribution of these subcumulus follows, has an index of less than 2, so their dynamical effects are going to be dominated by the most massive substructures, that is, these subcumulus when they're impinging on the galactic disk. Stelios has on to this and studied the effects of CDF substructure on stellar disks and found some interesting effects like this thickening, flaring, surface density excesses, etc. However, it is the coldest component of the galaxy that is the most responsive by the ratio of the inverse sound speed squared of the gas is colder than the stars. So for this reason, you can really maximize the rate of detection of dark subcumulus by looking for their tidal footprints, if you will, on the extended H1 disks of galaxies. The other reason the gas is great is because it has short-term memory. Okay? Disturbances in the gas disk can add about on the order of the dynamical time. So one of the most important features about these observations is the fact that you see these disturbances now. Because if they happen significantly in excess of the dynamical time ago, they would not persist in the gas disk. So it's sort of like this movie Memento, where this guy, he had memory loss, he couldn't remember things for more than a day. So you go and beat him up, and a day later he'd be your friend again because he just can't remember. So it's great. The gas has short-term memory. Okay, so it can't. If you see it, it's because it happened about a dynamical time ago. So as I said, I'm going to start with the proof of the principle of the method. I'm going to apply this to galaxies with known optical companions from the THINGS survey. So THINGS is surveyed nearby spirals, about some 40 of them, and this is a BLA survey producing H1 maps of nearby spirals. Okay, so this is the H1 map of N51. Okay, you see this broad H1, broad asymmetric N51 arm here. This is the optical image of N51. You see the perturber is sitting at the tip of the short arm. The metric of comparison that we're using to find which simulations best fit the data are the local Fourier amplitudes. Okay, I'm showing that for the data here. We're only going to focus on the low-order Fourier modes. So we're minimizing with respect to the local Fourier amplitudes between the simulations and the data for all time snapshots for a given simulation to see what best fits the data. So let's do this qualitatively first, and we're going to do this in a little bit more detail in a moment. So this is one of the best fit simulations, and this is the time which best fits the Fourier amplitudes. As I said, the simulation is varying as a function of time. So this is a simulation of N51 interacting with a perturber, and this is the time which best fits the Fourier amplitudes. So note that you recovered this broad H1 arm as you have in the data, and the perturber in the real system, so it's the tip of the short arm, and just by minimizing with respect to Fourier amplitudes, we get it pretty close. It's not exact. I've marked the location near the cross, but we get it pretty close.
How did you choose the input parameters for your simulations?
We're doing this in moments. So hang on to the question. So a number of quantities have to be varied to see what best fits the data. I found a useful way of conveying that is on a variance versus variance plot. Okay, so I'm plotting here the variance of Fourier mode 1. Okay, so this is AN1 of our data minus AN1 of our simulation, whole squared summed over all R. Okay, and the same thing on the y-axis, except that I'm adding it all in a quadrature. Okay, so variance versus variance on both axes. On such a variance versus variance plot, the best fits are going to be close to the origin. Okay? Now, the nomenclature here is the number before the R is the mass ratio of the satellite that the primary galaxy is interacting with. The number after the R is the pericentric approach distance. So what you can see from the slide immediately is that very low mass satellites, 1 to 100 mass ratio satellites that don't come close enough to the galactic disk, they're giving you very poor fits to the data. And it turns out that a 1 to 3 mass ratio satellite with a pretty close pericentric approach distance gives you the best fit to the data. Our determination.
At some time,
Excuse me? Say again?
At some time you're finding?
Yes, that is about to come up in less than 30 seconds. Okay, so you guys are anticipating the order of progression very well. Our determination of the mass of the satellite, that is a 1 to 3 mass ratio perturber, is very close to what is observationally inferred for the companion of M51. Now, as you just said, even the best fit simulation is varying as a function of time. It's varying as a function of time because the disturbances in the gas disk gap out on the order of a dynamical time. And this is very important, okay? This variation as a function of time is very important. Okay, because once you've found the best fit time, that allows you to find where the satellite is in radial distance now, and where the satellite is in azimuth of distance now. So constraining the time of encounter is very critical. So
there's mass ratio, there's information, there's
so we're gonna do that in detail.
Time.
Absolutely, absolutely. There is a slew of parameters, and we're going to go into that when I talk about the Milky Way analysis, and I'll show you how that can be encompassed on a variance versus variance plot. All of this information can be shown here, but I want to go through it in step by step. So you can convey how well different simulations fit the data on a variance versus variance plot, as you just said. Even a given simulation varies in function of time. So let me show you how this best fit simulation moves on the variance versus variance plot. Okay, so for some period of time, it's going to hover close to the origin, okay, and then it moves away. So I'm showing all of these here at their respective best fit times. And I'll address your question in a few minutes.
Best fit is closest to the origin?
Yes, because this is a variance versus variance plot. Okay, so simulation minus data whole squared, and on a variance versus variance plot, simulation minus data whole squared, your best fits are going to be close to the origin. The H1 map also gives you the phase of the modes, okay, which tells you about the shape of the spiral planform. And we actually get we derive the azimuth from the relative offset in the phase between the simulation and the data. Now, M51 is a pretty massive perturber. I've also tested this method for a galaxy with a much smaller perturber. This is AUC 1512. And if you carry out this analysis, you find that the satellite mass is about 1 to 50, 1 to 100. And that's also what is observationally inferred. So it looks like this method does work over a pretty wide range in satellite mass ratio.
Could you say a few words about the simulations?
So the simulations are done with Gadget 2 and they're initialized with an exponential disk of gas stars and live dark halo, and then you're throwing perturbers out. Okay, so you're varying the masses of these perturbers over a wide range. You're varying the distance close approach. You're also varying the orbital inclination, and you're varying the initial conditions of the simulated galaxy. And I'll show you how these other parameters, the variation in the initial conditions and the orbits, how they affect the fits to the data, and I'll show that specifically for the Milky Way. As you'll see in a moment, the dependence on these parameters is not very strong. And this, coupled with a point that I'm about to make, this is really what allows you to infer the mass of the satellite and pericentric approach distance and solve the inverse problem. If there was a strong dependence on these other parameters, you wouldn't be able to do it.
So your perturber being modeled as a point mass, or
The satellite?
yeah, satellite.
No. It's an extended body, and I'm using the same scaling relations for between concentration and mass that are in Masha et al.
It's a live perturber.
It's a live perturber. So in M51, for instance, these are the most detailed calculations, the simulation of M51 and this satellite, because this doesn't do that application.
Tidal loss.
Yes, yeah. So everything is live, all bodies are extended. So I want to spend a couple moments on an important theoretical point, which I didn't know the answer to when I started working on this, and as far as I know, it's the first time it's been pointed out in the literature. This question is, the tidal force goes to over R cubed. Okay, so there's inherent degeneracy between, say, a big perturber further out or a small perturber closer in. Okay, so the question is, can you really figure out the perturber mass? So what I realized is, let's say R naught is the minimum distance at which a satellite of mass ms first starts to raise tides on the galactic disk. If the time it takes to go from R naught to the pericentric approach distance is greater than or a quarter of the time it takes for the gas to shock in the primary galaxy, then you can break this degeneracy. Because then you get to capitalize on the nonlinear response of the gas along this low radial approach. Now, for satellites of smaller and smaller mass ms, their R naught moves closer and closer to the pericentric approach distance, resulting in an effective impulse approximation where you only feel the kick at one point. So here's the demonstration of the idea. Shown here, a Milky Way-like galaxy. Okay, the gas density images as a function of time, interacting with a 1 to 100 perturber with some pericentric approach distance. On the bottom, it's the same thing, but interacting with the 1 to 10 at the equivalent tidal distance as this 100. And so literally set is equal to Q, such that at their respective pericentric approach distances, they exert the equivalent tidal force. However, they elicit a very different response, okay? Because when you go beyond the impulse approximation makes the pretense that the primary galaxy does not respond as the satellite is approaching it. Okay, so if all I'm allowed to talk about is m over r cubed, then I can't break the degeneracy between m and r. Okay? But when you look at the time-integrated response, the satellites of different mass, this 1 to 10, has a larger R naught than this one. Now this, coupled with the fact, as I'll show in a moment, that there is not a very sensitive dependence on the initial conditions, these two things taken together are what allow us to solve the inverse problem. So now let's get back to the Milky Way data. So on the top is the raw H1 map of the Milky Way. Okay. On the bottom is the unsharp masked image. This is from Levine, Bliss, and Hylas in 2006. So unsharp masking is like going around in an azimuth and dividing by the median, which allows you to heighten those certain brightest features. Note that the solar circle is here. Okay. So these perturbations that you see here are really on the outskirts. The scale here is between minus 30 and 30 degrees C. And I'm plotting the Fourier amplitudes relative to the axis of under here, and you see that the low order Fourier modes are for 20 to 30%. Now, in an isolated galaxy, the stellar density waves travel between the inner and outer ring cloud resonances. In principle, gaseous density waves can go beyond these resonances, but their amplitude drops off because there's nothing out there to force the gas. So it's not that you wouldn't expect anything in the outskirts, but you certainly wouldn't expect things at the level of 20 to 30%. So we have to ask the question, what caused these structures well outside the solar circle? So I did a range of simulations. I'm showing the gas density response here on the left, stellar on the right, where the Milky Way is interacting with the dark subhalos. I varied the masses of the satellites from pretty low mass satellites, 1/1000 of the mass of the Milky Way, pretty massive satellites. I varied the distance close to approach. I varied the orbital inclination, that is it coplanar or is it polar. I've also varied the initial conditions of the simulated Milky Way. I varied the gas fraction between the range of a 10 to a third. I varied the equation of state, how much energy injection you have from supernovae, or is it isothermal, etc. So once you've done this parameter space survey, you basically have a Goldilocks problem. So you want to find what's not too cold, what's not too hot. Data is going to be on the right, simulation is going to be on the left. You have these Milky Way-like simulations interacting with perturbers of mass 1 to 300 or lower. Their Fourier amplitudes are too low relative to the data, so this is too cold. This interacting with perturbers that are 1 to 50 or higher, the Fourier amplitudes are too large relative to the data, so this is too hot. For interactions with 1 to 100 mass ratio satellites in fairly close pericentric approach distances, we get a reasonable printed data, so Goldilocks is happy and she can comfortably keep her porridge. So let me show you this is again the gas density, which is a function of time. I've marked the locations of the center of the Milky Way and the perturber here. You have a pretty close pair to approach distance. You see the main response about a dynamical time later when the perturber is about 80 kiloparsec away. Okay, so now let's get to one of the questions that came up, which is that a number of parameters are being varied. You already discussed that when you go beyond the impulse approximation, you can't range the degeneracy between M and R. However, there are other parameters, such as the initial conditions and the orbits. So you have to ask the question, what is it that really matters? What drives the fit to the data? Again, I've found one way of conveying this information is on a variance versus variance plot. So this is variance of Fourier mode 1, simulation minus zeta whole squared on the x-axis, variance of Fourier modes 1 through 4 added in quadrature on the y-axis, simulation minus zeta whole squared on both axes. So best fits are going to be close to the origin. Same nomenclature as before. The number before the R is the mass ratio of the satellite. The number after the R is the pericentric approach distance. So immediately you can see that the Milky Way cannot have experienced interactions with 1 to 10 mass ratio satellites. In anywhere near a dynamical time ago, they're very poor fits to the data. All of these points here in green are the very ends of 100.5. Okay, so I'm fixing here the mass ratio of the satellite, and I'm fixing the pericentric approach distance, but I'm varying everything else. Okay, so I'm varying the initial conditions, I'm varying the gas fraction to within the range of the 10th to a third, which is reasonable for local spirals. I'm varying the inclinations. I'm also varying the equation of state, okay, whether it's isothermal, you have energy injection from supernova. Now, as you can see, they're not all the same. Okay, so initial conditions do make some difference. Okay, they do matter a bit, but they all cluster close together. Okay, and they all cluster close to the origin. Okay, so I have to conclude that this problem is pretty robust to variation in initial conditions. It's not very sensitive to the initial conditions. 4 parameters comparable to spirals. I should point out, it is the case that if you increase the gas fraction in excess of 50%, then this error circle, if you will become larger. The parameters comparable to spirals is not very sensitive to initial conditions, and this is what allows us to do the inverse problem.
Is that because of high gas fraction of the spiral, the galaxy on its own won't develop this spiral?
Well, I mean, it's just generally going to be more unstable depending on the equation of state. So you can think about, making a plot which has 2 axes. Okay, gas fraction going this way, equation of state going this way. Okay, and at low gas fraction, there is a huge dependence if you're varying equation of state. Okay, but at high gas fraction, you go from isothermal to energy injection, a lot of energy injection supernova, you affect the stability of the gases. This is actually less the case on the outskirts, and I'll show that in a moment with respect to the other measure of comparison that we use, which is the phase of the disturbances. Because there's very little, most of the time, what people do in simulations is to adopt, say, something like the spring-on-purpose method of that, which takes the energy injection rate from the supernova to be proportional to star formation rate. Right? And there's very little star formation in the outskirts. Which is why, even though feedback, star formation, etc., are not modeled well in global galaxy simulations, if you go to the outskirts, you're going to do better than if you go to the simulation.
So is that mass ratio, what is that number actually, right? So that's the ratio between the satellite mass and the mass inside by PBC?
No, it's total mass of both galaxies.
Okay, that's in our case. Milky Way is like 10 to 12 or something.
Right.
And so the satellite is 10 to 10 mass perturbation inside of 5 ppc.
So between 5 to 10 ppc.
So that's a sort of like comparable amount of mass that we have inside of 5 ppc. Right? So it's hard to
mass in this, mass inside.
Oh, okay.
It's just
it's a stellar, it's a baryon mass talking about, for example.
plus the and then whatever's that going to pass.
Yeah, I mean, and so I mean,
That's my question.
Is this only 2 things?
A lot of my questions.
So you're talking about halo masses.
I'm talking about
Both of them are halo masses.
Well, and it is the
So
total
Neil's concerned
mass.
about that the 10 to the 10 is a fifth of the mass of the Milky Way inside.
It'll be changed over.
On the other hand,
What's the mass of
so
satellite in solar masses?
10 to the 10, she said.
it is about 10 to the 10. So let me answer the question.
How big is, how big?
That is the relevant question to ask. How big is it? It's not just the mass, it's also how big is it. So if you have a puffy system, right? If you have a bullet, it's gonna, you're gonna get much more different. But if you have a puffy system, the most that you can impart is the escape velocity. And for 1 to 100 halos, your escape velocity is of this order of the stellar velocity dispersion, which is why, even if you hit it, okay, you have a restoring force you have a restoring force that effectively stabilizes it. Which is why such interactions, and this is also found by studies Azimuths and Christopher Sell and James Pollock and others, that is 1 to 100 interactions with close period-centered approach distances, less than 10 kpc, do not violate, because of the puffiness, they do not violate the observed thinness of the Milky Way.
So the way to say this is, what's the mass still bound to that small halo when it gets that close in? Because it's being stripped on the way in. What's the virial radius of your satellite?
So, I mean, it's several kpc.
And as it comes in, how much mass is it losing?
You're losing some mass, but I don't think that's, I don't think that's the critical,
Like it's puffy, you're saying, right?
It's the puffiness of it.
So therefore losing a lot of mass, right?
You're losing mass beyond the tidal radius.
Exactly.
And I think we've done this calculation. You're not losing I don't know exactly what it is, but I don't think you're losing that much mass in terms of how it's affecting. Well, we can go over this in more detail, but if I remember correctly, the tidal radius is something like a few kpc, so you're actually not losing that much mass. What's really critical here is, how much of the kick are you giving?
So it's much denser, you're saying, right?
Yeah, that's what I'm saying. That's what I'm saying. Yeah.
And so it's therefore, like a bullet.
No, that's exactly the reverse of what I said. Okay, so a puffy thing is the opposite of a bullet, right?
Okay, so if it's puffy,
yeah,
you should be tidally stripped, right?
you're going to tidally strip it beyond your tidal radius, right? And so you have to compute the tidal radius. And my recollection is that you're not stripping a lot of mass off of it, but I should say that the stripping is that how much mass you're stripping off is going to affect, say, if you were to go and look for it now, right? That's going to affect the detailed calculations of the structure of the dwarf satellite.
One simple way of doing this is that, for example, there must be an equivalent point mass perturber at the same percentage radius, which does the same amount of damage. That's the mass going up. We don't want to close these masses, which are within sliding of 30, 40 kiloparsecs, or something that has a percentage mass of 5 kiloparsecs. We don't know what mass when it's talking about. It's just enough.
No, but the rear radius is for the same. It's not 30, 40 kpc. It's like
You see two keys from dark matter to cold matter.
Yeah, but it's several.
Then to the tensile mass, because they're what's the critical.
No, I don't think
So
it's
it's 5
at
times
most
more.
it's at most 10 kpc. But okay, we can.
Ways 300
Well,
kiloparsecs, but it'll be much more.
Well, we can check the numbers in
We know the
detail.
numbers.
Check the scale radius is that, right? So it's that similar to large magnetic cloud, right?
Or Sagittarius.
Yeah.
It's similar to Sagittarius.
Those are factors of any difference.
So, but we don't care about luminosity. We don't care about mass, right? We care about velocity. So
Sagittarius is much smaller than
That is 10, that is
No.
7.
There are a number of estimates where the mass of the total mass of Sagittarius is not most.
It's very small.
No,
Compared to the LMC, it's very small.
it's the rotation curve of the LMC is pretty wide. Okay, so
But the overall amplitude of
it is true the LMC is more gas rich. It's true the LMC is more gas rich, and it is a bigger system. It is generally believed to be a bigger system than Sagittarius. However, by several times, possibly. People who model Sagittarius, okay, including Catherine Johnson, James Pollock, and others, many of the early estimates gave you lower numbers, okay, like say in total mass, a few 10 to the 9. Okay, very recently, James and I have just submitted a paper where what they're using is a somewhat larger mass for Sagittarius, which is about 2 10 to the 10 solar masses. Now, I should admit, I haven't followed the details of their calculation of the mass of Sagittarius, but I think there is a wide, range in the masses that are being cited for many of these dwarf galaxies because their total dark matter mass is hard to estimate. Okay, so we're gonna leave it at that because I want to move on. But if you want to talk about this more, we can come back.
You know what you chose in your initial conditions. You know what you chose in your initial conditions. So regardless how much the interacting mass or the stripping is, you can describe the results in terms of the initial conditions.
Right.
So one of you just call this the mass of the initial state.
Sure. Yes. But I've seen, generally I've seen the numbers for the mass of Sagittarius that are cited, and it's not just James's papers. There are other papers recently that have come out that have cited masses, 4 to 10 to 10, a couple 10 to 10 solar masses. But it's true that numbers that are being cited for Sagittarius earlier were on the lower end. But I just can't speak to that. I don't know the detailed modeling for mass estimates for Sagittarius.
We've done the modeling. You take surface losing mass now, therefore it must have been stripped of most of the dark matter. Because it's been stripped of most of the dark matter, you cannot tell what is the original mass of the Sagittarius.
Sure.
You never will be able to tell. So we lost it all.
Yeah, no, this is
So that is where the uncertainty comes in now. Today, the mass is quite low. And mass of the star is quite low as well.
Of course.
So you compare
Yes,
that with
they're talking about the initial.
sure.
They're talking about the initial mass. They're talking about the initial mass of Sagittarius, not the mass today, obviously. Okay. All right. I want to address an important question, and so James has actually, at his student Christopher Sell, we've actually done this calculation using the initial state of Sagittarius, obviously not the state of Sagittarius presently, but the initial state of Sagittarius, and they've gone ahead and done that calculation to see how it affects the Milky Way disk. So we can talk about that in a moment if you're interested. But another important thing to ask in this context is, can the Large Magellanic Cloud be the culprit that produced these disturbances? Okay, because it's a pretty massive system. It's a border 10 to the 10, or maybe a few 10 to the 10. It could be, obviously it's further away, so it's not lost its mass. I don't think there's any disagreement on that question. And yes, the present mass of Sagittarius is less than the initial mass. But it is pretty far away. Okay, it's about 50 kiloparsecs away. So I'm showing here a figure from Chakrabarti and Loeb. Okay, they've calculated the orbits of the LMC, taking the copper motions as a constraint. This tick mark here is 50 kpc, and they varied the potential depth of the Milky Way from 220 kilometers per second to 265 kilometers per second. Okay, and as you can see, independent of the variation of the potential depth of the Milky Way, it cannot have come closer than 50 kpc. Okay, now for deeper potential wells, it could have had multiple approaches, but regardless, it cannot have come closer than 50 kpc. So just gone ahead and done the experiment here. And let me just say this is roughly a 10 to the 10 solar mass perturber. I'm not going to nail it down closer, in more detail than that. But when it's about 40 to 50 kpc away from the galactic disk, it's just too far away to raise appreciable time on the galactic disk. Okay? If it has a close periodic approach distance, you may see a response comparable to what we're seeing now, but you really need to have a close periodic approach distance. So based on this calculation, I have to say the LMC cannot be the culprit that produced these disturbances. Generally it is the case that it is said to be a larger perturber, obviously, than the Sagittarius now, but in initial state, the initial condition of LMC could easily have been as massive as Sagittarius, according to a number of estimates. Yeah, go ahead.
How confident are you that it was the effect of one perturber that did this versus more than one?
Let's talk about that. So there are a number of distributions that matter when you're analyzing these type of disturbances. There's the distribution as a function of mass. There's the distribution as a function of where these satellites hit the disk, and there's also the distribution as a function of time. Okay. Now, if you're looking at disturbances that are, say, produced by satellites less than 10 to -3, they're not going to give you, enough signature. If they don't come close enough to, say, a few scale lengths, a few times the scale length of the galactic disk, they're not going to produce enough of a signature, as you just saw with the LMC. And the final thing is, let's say you had multiple perturbers like you have in cosmological simulations. Generally, they're not impacting the disk. Of course, there is no disk in cosmological simulations. But let's say there was, okay, let's say they did impact the disk. Several of them within a dynamical time, okay? It's still the case that the first cut is the deepest, right? Because after you have this first big impact, the gas heats up, it becomes less responsive. It just doesn't want to respond as much after that. So the subsequent response after that is sublinear. So because we're looking at gas, it is a little bit easier to, I think the case of multiple perturbers should be treated in more detail than we've done, and we're starting to do that. But it is a little bit easier to deal with that because it effectively just will contribute a low level of noise. The other way you can look at it is by looking at the coherence of the phase of the mode. So if you had a bunch of perturbers that was impacting the galactic disk, the phase would be kind of patchy. This is the phase of the modes of the H1 data in the Milky Way disk. It's not very patchy. It's pretty clear. But it is an important question to look into. My feeling is the other reason is when you look at the effects of if you have a distribution of some halos, and if that power law of that distribution follows is less than 2, then dynamical effects are going to be dominated by the most massive perturber, right? So that's one thing, and then, as I said, unless, with gas particularly, if you're looking at things now, it means it has about a dynamical time here. And even if you had multiple impacts within a dynamical time, the effect is not going to be, it's going to be less than linear. So the other metric of comparison that we're using here are the phase of the modes. This is to determine the azimuth of the perturber. So I'm showing here the phase of modes of the actual H1 data because the image is not just the Fourier amplitudes, the Fourier amplitudes plus the phase. So this is the phase of the modes from a couple of the best fit simulations. I'm varying here the equation of state from isothermal to an equation of state where you have energy injection from supernovae. I know if you're looking at this one, that this is the isothermal one because it has a higher density contrast in the inner regions. But what I want you to notice here is that they're very similar in the outskirts. Okay? Why is that? We already talked about it. It's basically because in this multi-phase ISM, you take the energy injection rate to be proportional to the star formation rate. The star formation rate in the outskirts is very low. Okay? So that's why this other metric of comparison that we're using to determine the phase is robust to the variation of the equation of state, a parameter that we don't know.
But I'm a bit lost here. What are you showing? You
So
said this is the best phase, so they look for the best phase of what?
Excuse me?
These are the shown of the best phase.
This is,
But they're very different, so the
Are
best
they
phase
very
is different down the top and the bottom.
this is the M=1 mode. Sorry.
One versus
This is M=1 and this is M=3. Sorry.
Different modes of n for the same best phase one.
So yeah, this is M=1 for
Same gas
two.
distribution.
So you take sigma
It's
bar.
two different simulations.
Yeah. This is one simulation. This is M=1 and this is M=3. This is the phase of the M=1 mode. This is the phase of the M=3 mode. Okay, this is for one simulation. This is the phase of, okay, and this is another simulation. Both of these fit the Fourier amplitudes of the data well. And the only point that I want to make here
No,
is...
I think I understood that.
Okay.
I was confused with what.
Okay, great.
What was the problem?
So, yeah, the point is that, the phase in the outskirts is pretty similar when you're varying the equation of state. That's nice because this is the metric that we're using. If we had a huge dependence on the equation of state, it would be difficult. And as I said, things like star formation, energy injection from supernovae, modeling the equation of state, these are things that we don't understand well. And they obviously will affect the inner regions of galaxies, where the distribution between, say, atomic and molecular hydrogen, these are things that will affect the internal structure of galaxies significantly. But when you go to the outskirts, you don't have to worry about this so much because it's H1 dominated, very little star formation. There's very little energy injection, so you have to be careful. All right. This is just the line plot of this. And I'm showing a range of simulations here. And as you can see, they're all very similar in the outskirts. There's a sharp gradient in the phase in the inner regions where you have self-excited spiral structure. Self-excited spiral structure produces tightly wrapped arms. You want to think about walking along these arms. If you have tightly wrapped arms, you have a sharper gradient in the phase. Tidal interactions, which tend to produce open arms, have a flatter variation in the phase. If it's an open arm, it's not going to have a sharp gradient. And it's also the phase in these tidally interactive simulations is quite different from that of an isolated galaxy. Now, I'm just showing here a movie of the phase of the M=1 mode as a function of time in the black dots. Okay, it's varying as a function of time. I've overplotted in red the phase of the M=1 mode from the data. Now, I'm showing the same thing here, but at the best fit time to the Fourier amplitudes. Okay, so the phase of the M=1 mode of the data and the phase of the M=1 mode from the simulation at the best fit time. As you just saw, the phase is varying as a function of time. It so happens that at the best fit time, the phase is flat in the outskirts. Okay, this is the time which best fits the Fourier amplitudes. Now, a priori, these two constraints, the Fourier amplitudes and the phase, are completely independent of each other. But in a model of an external perturber, they're related. Okay? And so the phase also gives you an independent means of constraining the time of encounter. And so it turns out that they give you roughly the same time. It's at the time which best fits the Fourier amplitudes of the phase is flat in the outskirts, which is a very compelling, which is good evidence for tidal encounter. And you see a sharper gradient in the phase in the inner regions. Okay, so I've put these three things together. The Fourier amplitudes, the three constraints. I'll explain the third one in a moment. The Fourier amplitudes, the phase. And there's another one, which is an asymmetry in the radial velocity. This is the observed quantity here. This is you see the radial velocity is increasing outwards. This is what you would infer from the observation, such that you don't have a discontinuity in these wedges on either side of L0 and 180. Now, you can go to your best fit simulation and try to find the angle. I'm plotting the radial velocity in the simulation as a function of angle. And you can try to see where the radial velocity, at what angle, you minimize the comparison to the radial velocity in the data. Okay? So the minimum in this gives you another measure of the azimuth. Okay? The way we're actually getting the azimuth from the phase, I don't think I quite explained this, is from the relative offset in the phase between the simulation and the data. Very roughly speaking, it's like taking two transparencies and aligning them with respect to the dominant features. Okay, I've gone ahead and put these three things together and made a prediction for the azimuth in this perturber, and this is where it is, between roughly L of -10 to -50. It is a prediction, so I don't know if I'm right or wrong, but there are plans to look for it. Potentially the way of looking for it is in the near infrared, where you're less affected by dust obscuration. Yes?
What are the blue dots?
These different dots are, what you infer from the, fitting to the various modes. Because they're, it's not just the M=1, you can get M=3.
You predicted more than one perturber? I didn't understand that.
Say again?
You predicted more than one perturber? Or?
No, this is just what you get from, you can look at the relative offset between M=1 for the simulations and the data. You can do this for M=3, etc.
You don't get the same position?
No.
More than one perturber, but it doesn't work.
I mean, it's pretty.
Blue and red.
The blue and the red. Well, and
Blues and red.
No, yeah, that's M=1 and M=3, right?
yeah, but I'm not claiming we have. I'm not claiming. So I'm not claiming we have a perfect fit to the data. Remember, when we looked at the variance versus variance plot, we were not at 0. Okay, not a perfect fit for data, and no such attempt is being made to obtain a perfect fit for data. I leave that to people who are superior than me to obtain a
And
perfect
your
fit.
error bars are bigger than they were on Netflix, right?
Oh yeah. This is, I mean, of course, that's an inspiring example, but I mean, that problem is in many ways similar to your Galaxy problem, the multi-component system.
But these strings are also know that, right?
Yeah, I want to address this question first.
Okay.
Hold on a second. So if you had really a perfect fit to the data, then you can expect a better correspondence than I have between the offsets of the different modes. The other reason that there is a variation here is because I have allowed the initial conditions to vary. Go ahead.
Oh, no, yeah, okay, well, right, yeah, so these streams that we know about, like, for example, with Sagittarius or the Orphan stream, right? Where are they relative to these?
Sagittarius is about 14 degrees off the plane, and
The stream, I mean.
the stream. Well, I mean, it's about here somewhere. Well, you would know. Am I pointing to the right place?
It's
The stream, I think.
polar, so. So I thought it was just behind polar. It's up to polar.
Oh, it's behind the belt of Sagittarius, okay. Is the Orphan
Well, it was found by
No,
taking
no,
cuts.
no.
It was found by taking cuts in the galactic bulge.
So it is behind the bulge.
Yeah.
The stream is almost polar, right, so.
Yeah, I actually have an image where from 2MASS which shows that stream. So I can show you later. But
The Orphan stream must be also.
this is, Sagittarius is, we have actually done this calculation, or rather, Chris Witzel has done it. And if in their model, Sagittarius is, again, the initial mass, of course, not the present mass, the initial mass of Sagittarius is, in their heavy Sag model, is about a couple 10 to 10 solar masses, and its periodic approach distance is, I think, almost 20 or 25 kbc. So the earlier models in Sagittarius that Johnston and Zalupton had even an initial mass being lower, and they didn't come as close. But even in their model, which is the heavy Sag model, and they're coming closer, they just don't produce, if there is a one-to-one correspondence between the N volume of one information that they've done and the H1, which we don't necessarily expect. But assuming that that's the case, you still wouldn't get enough power in the odd modes to explain the H1 data. So I think a more detailed calculation needs to be done to do a full hybrid with Sag. But that's what you would get. So Sagittarius, it seems, would not use the observed disturbances in the H1
So you're showing your things in the plane.
Yeah.
Why?
Yeah, so in the first paper, I didn't make that restriction. In the first paper, I looked at very orbital information. But if you're talking about the Azimuth of an effectively dark satellite, a pretty massive one, then just do the possibility of using some of those. Otherwise, you would see. And I've gone through the census of known Milky Way satellites that could have used it, right? So it's.
But there's Canis Major that people talk about, which is on.
Canis Major is an interesting case, absolutely. Canis Major is also in the south, and Jorge Penarrubia actually was written a paper sometime back. It's I don't fully have to say I don't fully understand the case of Canis Major. Some people don't really. I think there's some disagreement as to whether it's real.
No, I understand this agreement. I just was wondering where in your plot here.
It's actually close to this. It's actually close to this. I think
it's
it's
the right side of the.
Yeah, it is. It's around here somewhere. I don't remember exactly where it is, but it is in the south, and so that's worth looking at in some more detail. I don't know if it's quite. And again, there will be stripping, so there's going to be. There's going to be a difference between initial mass and current mass. But even taking that into account, I'm not sure that Canis Major would be quite massive enough. So I don't know, but that's something definitely worth looking into. But we have looked at LMC and we have looked at Sagittarius, and neither of those could be, it seems. So Phil, of course, has worked on this problem as well. And our approach, am I running out of time?
No, you're fine.
Okay.
Give me 10 more minutes.
Okay. So the approach here was, these hydro calculations are being done with millions of particles, so they're a little expensive, so we wanted to do a more simplified approach. So one thing is to look at the disturbance, think of this as a bunch of test particles and look at the disturbance that they're excited by passing some halos. Another way is to think of the disk as a bunch of rings experiencing N modes. And these subhalos are very light compared to the primary galaxies, so what you can do is linearize the equations of motion, expand it as you value theta. And it turns out both of these approaches give you very similar results. And you can come up now with scaling relations between the effective Fourier amplitude and the satellite mass ratio. It turns out this scales very simply. The goal here is, to take observed H1 mass and to be able to read off the satellite mass ratio from these H1 mass.
So what's it called? Mass ratio versus what?
This is the effective Fourier amplitudes, which is kind of like a sum over the modes.
Some overall power amplitudes and modes average out like a number of modes that summing over, and then just calculate for a variation of basically the orbit inclination and different angles of attack onto a disk impact site, okay? And then vary just the mass itself. It's just a measure of how uniform the gas distribution is.
Notice one thing, even gas system, I really care about basically how much disturbance I raise to this.
It's total power.
There's just total power. Right.
With zero if there were no difference.
Yeah, zero being no. But that will be very interesting.
Okay, so I guess I'll do this very quickly. Let's see. Let's just do it quickly. So, so far we've looked at the dynamics. Another measure, observation quantity you can look at is the infrared UV through infrared emission, which I've done earlier for much brighter systems. There's some millimeter galaxies and ULERs. So using my Monte Carlo code RADISH, which stands for rate transmitted particle hydride Eulerian codes, you can basically just take the SPH quantities as input, okay, like your density distribution, your locations of star particles, etc., calculate the emergent spectrum, or calculate the images in various bands. I mean, this is for some millimeter galaxies. It varies a lot as a function of information on the short wavelengths because different microseismic counting. Now, for spirals, many local spirals show copious PAH emission, which are these mid-infrared spectral features here. They recently implemented this. You would expect to see a correlation with new star formation, and these PAH molecules are excited by UV photons. So I'm showing here the locations of new stars, and this is not, if you have a little bit more contrast, you see that there's a low, kind of a low level of new star formation, a tail of new star formation here. And when you calculate the SU, you do see enhanced PAH emission. So this may be a model for these extended UV disks that people have been talking about. So in closing, let me just make a couple points. Our method is sort of analogous to lensing because it doesn't rely on the optical light. Lensing, of course, is subject to uncertainties in the projected mass distribution. If you're not, this is a proof principle from the Jetty et al.'s lens system. This is a known work, and they're able to infer the mass of the system pretty well. I want to go back to this inspiring example. Obviously, Leverrier was galvanized after his successful discovery of next-shoot. However, he then spent the rest of his career looking for Vulcan, which he believed was responsible for the creation of such a mercury. We now know today is not the case. Now, when I think about the difference between the 1800 and now, it's really this explosion of data. All Leverrier had was the solar system. These days, it's common knowledge that there are galaxies beyond our own, right? So the goal now is for us to apply our tidal analysis method on the entire thing survey to understand the statistical viability of the method, okay? Because there could well be a large incidence of false positives. Okay, it could well be that the cases I've looked at so far are poster child examples, and because of various caveats that we can talk about, the method may not work very well statistically. On the other hand, we could get lucky and it could well work. We could have a low rate of false positives. So this needs to be determined. We're right now in the process of supplementing the BLA data with single dish data for the entire sample because it was difficult to do this analysis. A number of these systems are missing diffuse emission on large scales, and supplementing it with single dish data will fix that problem. So let me go ahead and summarize. I find that analysis of perturbations in the cold gas on the outskirts of galaxies allows you to constrain a number of important parameters about the satellites, whether they be dark or luminous. Namely, you can constrain the mass ratio of the satellite. This is, of course, the initial analysis we determined. The current radial distance and the azimuth. So it's basically a new method to characterize satellites. I've tested this method for satellites over a very wide mass ratio. I should say, however, we need to do more testing with respect to a large sample to determine how valid this is statistically. Of course, we don't know what the nature of the dark matter is, but it is pretty clear. At least it does respond to gravity. It seems to be pretty clear. The cold gas is one of the best tracers that we have for gravitational cold that dark signals exert on galacticus. Thank you for your attention.
Time for a few questions on this.
Yeah. No.
So, looking at the same survey, any of those galaxies look like they haven't had an interaction?
Not a large fraction, but
Is there a characteristic age time since the last interaction?
yeah, I just haven't done it. We've been hampered by the fact that when we're missing diffuse flux because these are BLA observations, and for some of them, and then there's also some of them are it's a mosaic of different pointings. So right now we're in the process of getting single dish data. I think having that single dish plus BLA, getting the final data product will give us a really fantastic sample to answer these kind of questions. But because of the quality of the data for a number of systems, even though it's very high resolution, when you do have data, you're missing diffuse flux. So especially in the outskirts, you're doing the analysis of the outskirts, it is a problem. But,
It seems that the whole idea is predicated on the fact that disturbances in the outskirts, casual space, must be due to these type of interactions. What if they're not? What if it's just, gas clouds that are coming into the galaxy, accretion of some sort, dark fountain, you think of many things that will make this quite hard. So I was a bit discouraged when I saw your model of M51 where we have a good gut feeling that these major features of these are being driven by the interaction. In fact, you don't get the position of the azimuth right.
what do you mean? We got it pretty good.
It seems that it was the main arms were in the direction.
No, let's look at it again. Go again. Let's go back. No, I think we do M51 pretty well.
Anyway, but my question is, have you thought about other?
No.
Maybe I'm not
No, we're going to take a look at M51. So the arm is going in the right direction, okay? The perturber sits at the tip of the short arm here. Okay, so it sits right here. And it is close, very close to the tip of the short arm. It's not exact. The other thing I should point out is if I vary initial conditions, I'm always going to be in the right quadrant. Okay, so, and I'm not using any other information here. This is totally blunt, just using the Fourier amplitudes. So I think we do M51 pretty well. We do 1512 pretty well as well.
I think tricks out, I think he's a little confused because the H1, a big arm and a different scale in the upper.
Yeah, sorry, I apologize for that.
So,
I apologize for that. So you just ignore this. We want to talk about how this image at the best fit time compares to this image, and it actually compares very well, even the azimuth of the
It combines a little smudge in the middle of the two things, right?
That one right
In the H1. Where's the companion?
Beyond the
The
outside.
companion is
in the
right
left
here.
image, in the left bottom image.
It's right there.
It's right here.
Yeah, so that's what confusing about it.
Yeah.
It's the one at the top, is the one that appears most obvious in both plots.
Uh-huh.
That's the scale of the two.
Uh-huh. Yeah, no,
Go quickly
yeah,
for
the
it.
optical image is,
Okay.
of course, on a different scale than the H1 image, okay? So the perturber is here, if I can point, the perturber is here, if I can point. Okay, so it's not, it's
20
not,
degrees off.
yeah, it's not exact.
Right. So
Okay, and
how-
when I'm varying initial conditions, it also varies, but it's not exact.
So how confident are you that this features a set parameter to one will actually be due to foul constructions in the case where it is not obvious?
Okay, so let me answer that question. Okay, there are a number of caveats, okay? So it's correct to assume that these disturbances are due to tidal interactions. And when you're looking at the outskirts, it's a reasonable assumption to make. It's certainly not going to be due to intrinsic, self-excited spiral conduction, which is not going to be very much beyond the LR. What are other things? You said gas accretion. There's also possibly triaxial halos could produce these kind of disturbances. So these are probably the two most promising candidates, and that's something that I'm starting to look into now. I think what we probably have to do is to look at other observational constraints in addition to what we've looked at to try and come up with discriminants. In particular, to look at the velocities for accretion if you want to rule out accretion.
Vary the gas fraction of your perturber.
Sorry? Yeah, I have.
So
Yeah.
how much does that change?
Not a whole lot, assuming you're not varying gas fraction in excess of 50%.
It's a very small object, so it probably won't matter.
That's right.
It's just high.
That's right. So you're right. I have made that assumption. But making that assumption allowed us to carry this work forward. But it is very important now to go back and see how possible other effects, like say non-spherical halos, how they'll affect the outskirts, and they very well could. So let me talk about this with respect to the Milky Way, because with respect to the Milky Way, there are actually four constraints, and I didn't mention the fourth one, which is the warp.
I was going to mention that non-Leo, but I'm surprised that he actually go first to the work, then for the. Because these seem like secondary order stuff. I mean, it's very hard to match. Very clearly, low noise, big noise. The warp is there. We know there is.
Well,
we know how big it is.
no, I don't think.
And I explained that one.
So you're right. Okay, we're not matching things exactly, and we're not going to make the attempt. At least I'm not going to make the attempt to match things exactly, but we do have a pretty good fit, and we're able to back things out about the satellites pretty quantitatively without requiring exact matches. So I don't think it is in any way theory. Okay, but let me address.
Material, he meant features in the H1, not.
No, but I don't think the features in the H1. I mean, so things we're not. It would be ethereal maybe if we were trying to match to the features, whereas I'm really trying to match to a more global quantity. Okay, so
We have always under basic. What else is there to match?
well, okay,
Sure,
so-
you want to match 1 to 3 or something
But
like
the
that.
thing is, you're right. I'm not matching the high order Fourier inputs, right? Because I don't even trust the simulation to that level to match the high order Fourier inputs. For the low order Fourier inputs, what I'm summing over radius, right? Because I'm doing this variance versus variance plot, so I'm summing over radius. So it's AM1 of R data minus AM1 of R simulation whole squared summed over radius. So it's more of a global quantity. It's not like looking at these fingers of H1 in the outskirts. Okay, so now, but let me answer the question about the work. I've looked at the vertical disturbances, and you do get something like a warp in this model. The simulations are not as warped as the data. It's off by about a factor of 2. And I think that if you were to use, say, a non-spherical halo with a beta hat component, you would do better at producing warp. Obviously, the most realistic model is going to be something like the unified model, where you have some non-sphericity in the halo, and you have the effect of external perturbers. But for the reason that the torque is R cos X, you're not going to, with either one of these models, you're not going to buy yourself 4 out of 4 for these constraints. Okay, so if you buy yourself the warp and the asymmetry in the radial velocity with a offset halo or a non-spherical halo, okay, because the torque is R hat plus theta hat, you can give yourself a big Z hat disturbance. But for that reason, you're not going to fit the planar disturbances as well. Okay, so I think in the end, right now I'm starting to think about how we can come up with discriminants between, other mechanisms of generating disturbances in the outskirts, such as tracks, movers, and accretion. I think we'll just have to use other observation constraints, but it's going to be with any one model by itself. It's going to be difficult to by itself everything. I should say though that these halos, when you look at them, in reality are rounder than they are in cosmological simulations, and that's probably due to the inclusion of gas density.
Right, so I think we'll cut off discussion now. It's late, but let's thank you.